XMT, that is a transmitter, and this one is the receiver chem, that means the RCV to say this one is sync. Okay, so now this one, this is some sort of this format, source encode, encrypt, channel encode, multiplex, pulse modulate, bandpass modulate, frequency spread. It's top lines actually, and multiple access. They basically denote some sort of a signal transformation from the source to transmitter. This transmitter means this one XMT. Okay, this is just XMT is just a standard name, and the lower block is the signal transformation from receiver to sync and essentially reversing the signal processing steps. That means you have a forward transformation. That means y equal to, say this is, if it is y, if it just linear, say y equal to say maybe g of f of e of d of c of b of something like that. So that means you are doing a 1-by-1 transformation, and you are just doing the reverse transformation on this line. Okay. Now basically that we told that modulator demodulator block, we say that modem, and in a simple way. And if you see if you just modem often encompasses, that means several signal processing steps. That means modem means this modulate. This modem means, please try to understand that this modem means I am talking about this one and this one. Okay, this is some sort of a modem. Okay, so they do a lot of signal processing over here, and it is some sort of, you can say it's a brain of a system. And the transmitter receiver, this XMT and RCV, they are considered as some sort of a muscle of a system. Okay, that means they finally energize the waveform so that it can cross the channel and receive at the other side. So some sort of, in a control philosophy, you can say these are the actuators. Okay. So anyway, so that means this is some sort of a muscle and this is some sort of a brain. It means if you say in a very crude way. And for wireless applications, mainly we talk about wireless application. The transmitter, this XMT, these consists of some sort of a frequency up conversion stage to a radio frequency, some sort of 2.4 gigahertz level you are transmitting. So there actually you have the band and a high power amplifier and an antenna. Okay, so that means these are the, inside this XMT you have a frequency up conversion. Okay, so it is frequency up conversion. You have some sort of a HPA and antenna. And in this receiver side, you have similarly you have the receiver antenna. You have a low noise amplifier. This LNA. Please remember these terminologies are quite important. This LNA is the part of this receiver actually. Okay, antenna and low noise means amplifier, and you have a frequency down converter kind of thing from gigahertz to somewhere here you are playing in the megahertz level. Okay, in this zone maybe you are playing in a megahertz level. Okay, now let us again move from the source actually. So I think that means first you understand this is some sort of a bit stream over here. This is all bit stream. This pulse modulation gives you some sort of a pulse-like electrical waveform. From pulse-like electrical waveform, because from there, if it is wireless, then we do some sort of a sinusoid-like waveform with higher frequency. Then you have some sort of a frequency spread, multiple access, mainly security aspects of it. Okay. And then that sinusoid like some sort of a megahertz level waveforms to here maybe gigahertz level waveforms. Now from these gigahertz level waveforms to frequency down converter, then you again get it to megahertz level. From here you just create some sort of a hertz or kilohertz level things. And from detect means you generate this bit. You see that here small t, that means a continuous waveform. Here after sample it is capital T within bracket. And here it is some sort of a UI hat, that means bit stream kind, bit stream, symbol stream, whatever it is. Okay. So this is all symbol. Finally, you are getting, this is your source encode basically. This is your source encode. This side, this is my digital interface, that binary interface. So that we talked about. Okay. And then it is the communication chain. And finally you are getting your sync, that means the audio, video, or whatever it is. Now this first of all, that this input information is converted to a bits. Okay, that means from here that we have talked about. That means say I have my source, I have I will discuss this what is formatting in the next class. Say I have got some sort of a digital input. This is some sort this is called M-ary message symbol, because these are the quite, this is bit stream. Please remember this is also bit stream. Okay. Or it may not be bit stream, it may be alphabets, means A, B, C, D, like that actually. Okay. So it is like that you are saying, you are just speaking out certain words, and from that I am just taking out one by one. Okay. So say you have said some sort of some word, means I am disgruntled by that means act that was shown in TV regarding the US elections, something like that. So it is that means you are just taking out one by I, then A, M, means all this. So that means you have some sort of a digital input, M-ary, which is some sort of a maximum 26 different characters, and maybe one space, you can say 27 different characters. And after this source encoding, you are just converting it to some sort of a, say, bits, say 0, 1 kind of thing. Okay. Now, this M-ary, or sometimes you say that means you are actually after formatting, you are getting that binary stream. That means you are from here also you are generating say 0, 1, 0, 0 like this. Either you are generating here, or after source encoding you are generating here. But anyway, so this must be a binary interface. That means if you don't, even if you don't do here this binary interface, but here you must have binary interface. Otherwise, it will not work. Now that first of all, that for it means this symbol, each message symbol. This is please remember this term is quite important. Message symbol M-ary. That if I have some sort of a say 2, 0 and 1, so then M-ary equal to M0 and M1. Okay. Now that means I have some sort of a first of all finite number of alphabet set. If capital means M-ary equal to say M0 and M1, that means capital M equal to 2, that means 2 distinct message symbol. This is binary and it is just constitutes a single bit. And sometimes what we do, that means not necessarily that I will do always binary, but sometimes I just group the bits together and I make say M1, say M0, M1, M2, M3, where capital M equal to 4. Okay, that means M0 to small m, capital M minus 1 kind of thing. That means I am just say in this case, that means I have this message, this one, each one is called symbol. Okay. Sometimes we say that one bit group together. That means that time bit is symbol, bit is same as symbol. Sometimes we say 2 bits grouped together. there are certain advantage and disadvantages of this grouping together. Okay, so that means sometimes 3 bits grouped together, then you have 8 number of things. Okay, 8 number of different symbols. Then your symbol and bit are different. Okay, if it is 1 bit grouped together, then it is symbol and bit are same. So otherwise, if you just group, then it is some sort of, we say it is M-ary communication. That means M-ary means M means if M equal to 2, it is binary communication. M-ary communication. Okay. Now that means symbols are made up of a sequence of 2 or more bits. Okay. Now for systems that use channel coding, that means, please remember, for systems that use channel coding means what? That means, first of all, this I have told, this gray shaded blocks, these are optional blocks. So that means I can use, I may use, I may not use. So that means for systems, say I am using channel coding, that means some sort of a channel coding, sometimes we say that error correction coding. Okay. So this, please remember that we talked about general form, that we said here it is source encode, then everything, channel encode, then channel. But you see now where I am breaking things. Now between source encode and channel encode, I have put an encryption block in order to enhance the security. But that was an optional block. So that's why I didn't show these things actually. Okay. So that's why I told, that means so the same name, it varies from context to context or from the resolution to resolution, at which level I am talking about, at which detail level I am talking about. Okay. So this channel encoding, basically that here, what I am doing from this message symbol, that means this is my MI with some transformation, that means here the channel symbol, that means the channel encoder output, we say in a different notation, some sort of a UI. That means say U0 to something, U3 or maybe different. Okay. So sometimes and please remember that that UI, not necessarily this M may be same. It may be U0 to U2, maybe 3. I am just so that means my point is that I am doing some sort of a transformation on the symbols and to get this channel symbol. Now channel, why do we do the channel? Why do we do the channel encoding? In order to make the system much more robust, so that even if there's an error in M0, M1, M2, M3, but this U0 and U2, U0, U1, U2, they are keeping some redundant information. Say just I am giving you an example. Say I am doing say 1 bit together. Okay, some sort of a, so that means M0 and M1. That means where symbol is same as message. What I am doing, instead of sending, I can do without channel encoding. But instead of that, what I am doing, first to what say I am getting like this. I am getting the bit stream, say 0, 1, 0, 0, 1, something like that. And that means I am doing, that means each one I am doing XORing and giving an output. And say it is like that, that means first 2 blocks I am giving an XOR and I am giving an output. Similarly, next one, again I am doing an XOR and I am giving an output. So that means and third one, I am giving the XOR of first and third and I am giving an output. Okay.
Sir,
pardon?
Sir, you're writing out of space actually. Yes.
What I am doing, I have say 0, 1, 0. Okay, 3 consecutive bits. I am doing different operations on these 3. Okay. Say I am doing first, I am generating first 2 XOR, then second and third XOR, then first and third XOR, then first and second OR, then second, third OR kind of thing. So that means from 3 bits, basically I am generating say 5 bits. Okay, so that means then what happened? Basically I am increasing the number of bits. Okay, so that means from 3 to 5. That means if there's, actually why do, and just like that we don't do these things. Actually there's a specific mechanism for doing that, which type of operation I should do on this incoming bit so that I will get my outgoing channel and channel symbol. So these are my, say, XOR, first, second XOR, second, third XOR, first, third XOR, first, third OR, second, third OR, something, say, first, fourth, first, third, and something. So these, whatever you are getting, different one you are getting 1, 0, say 0, all this. This one is UI. Please remember, this is my channel symbols. This XOR and OR, all this operation, that actually this is some sort of a channel encoding. Okay, so that means that number of bits before the channel encoding and number of bits after the channel encoding, that differs. Okay, now why do we do that? Actually that your general bit error rate, that will be reduced. Means bit error rate reduced means, actually if I do if I take the specific operations, then what will happen, even there's a channel nonlinearity, there is some burst error on the channel and all these things. There are two things. One is that from this data I will get some idea, that is when I do this channel decode, from here I will have some idea that no, it cannot be these bits. That means there one thing. One is that I can detect the error. That means I can detect the error means I know I can detect that there is some error, but I don't know what is the correct mechanism. And this is some sort of an error detection criteria. Another, sometimes even if we choose the means formula in a correct way, even we can correct the error also. So that means error detection and error correction mechanism. So I am doing some operation on this so that I will have some sort of a error detection and or error correction mechanism I have inbuilt into the bit stream. Okay, from the received bit stream only I can understand that whether it is error, whether I can detect the error, if there's error or not, if there is error. So if I have more number of complicated operation, I can even correct it. Okay. And when you are getting this first type of facility, what is the trade-off? Trade-off is you are increasing the number of bits. That means, say here with 3 bits, you are generating 5 different operations or 4 different operations and generating 4 bits. Okay. So that is the trade-off basically. Okay. Now, so this is my channel encoding. That means the formatting that transforms source information in bits, thus assuring that compatibility between the information and the signal processing within the DCS. And from this point up to the pulse modulation block, the information remains in the bit stream. That means from this side to pulse modulation, this one. So this whole one, that is basically bit stream. Sometimes if it is 2 bits grouped together, 3 bits grouped together, then we say, okay, this is bit, this is symbol and all these things. But physically if you check, it is all bit stream. Okay, there is no physical electrical signal or anything. Okay. So now from this point, that means this, see, till now this is bit stream. Okay. First you see I have written this is GIT. Okay, that means this is some sort of a waveform. And why the name pulse? Why the name pulse? Because this is a pulse-like waveform. Pulse-like waveform means something, say my waveform is like this. Say I am saying this pulse modulation, say this I am saying this is my 0, and say this is my 1. Okay, and say I am saying this is my actually 0 voltage, this is some sort of a say 2.5 volt. Can you, oh sorry. Say so it is a logical bit stream. So in the pulse modulation, what you are doing, say logical 0, I am defining as an electrical signal where it is a some sort of a ground 0 volt, this plus 2.5 volt, say this is minus 2.5 volt, and this duration is you are taking some say 0.1 millisecond or whatever it is, say 0.1 millisecond. And similarly, the logical one, you are saying this is my 1 and this is my actually 0 volt, this is 2.5 volt, this is this is minus 2.5. This is 2.5. This is minus 2.5. So that means this is a G0T, and this one you are saying say G1T. Okay. Now try to understand. Is this clear to you? That means that pulse modulate output will not be bit stream, will be some sort of electrical waveform. Okay, pulse like electrical waveform. Now now if you have some sort of say 2 bits grouped together, then you have 4 different symbols, and for that 4 different, say you have, that means more than 2, then you have some sort of a G0, G1, G2, G3 kind of thing actually. Okay, so generally we talk about say 1 bit group together, so that pulse modulation, and we are getting G0T and G1T. When you do this this 1 bit group together, yes, that means symbol is equal to bit, then see there are different mechanism, different way of representing logical 0 and logical 1 to electrical signals. Now there are this way of this conversion from logical 0 to logical 0, 1, logical bit means logical bit stream to the electrical pulse like signal. When it is binary kind of thing, that is 1 bit group together, then that is called PCM sequence. We will explain this PCM sequence in a detail. Okay, pulse coded modulation sequence. Please remember PCM sequence, or sometimes we say PCM, rather PCM waveform. Okay, because this waveform, that is G0 and G1, maybe I am defining 0 something like this and 1. So this is one PCM waveform. Okay. Maybe I am saying no, I will not do this. I will do my 0 is, say logical 0 is 0 volt, and logical 1, that is maybe 2.5 volt. Or so this is another PCM waveform. You may say no, 0, my logical 0 is minus 2.5 volt, plus 1 is logical 1 is plus 2.5 volt. So this is another PCM waveform. So there are different types of PCM waveform. Now just like you cannot take just like any PCM waveform, because in order to choose the PCM waveform there are certain guidelines actually. That means, because see, sometimes if it is not wireless, then these waveform, this G1T, G0T and G1T, basically they will go through this channel. Okay, maybe wired channels and kind of thing. So that means, see, through wired channel sending pulse waveform means you have to do something, and you have some other criteria that you have studied. We have studied those things in signal systems, signal networks class. So those things we will discuss. So that means when your 1 bit group together, that means when it's so it's a symbol equal to bit, that time that I will, for 0 I will just represent by 1 electrical waveform. For 1 I will define another electrical waveform, and electrical waveform should be defined in such a way so that at the receiver side it should be detected properly. It should be detected by ZT properly. ZT means that what is my output, means wave value kind of thing. Okay. Anyway, so that, and when you have some sort of a more than 2, means more than 1 to M3. Now that time what we do, that we do some sort of a means this, we say that M-ary pulse wave modulation. M means generally we say pulse amplitude modulation, sometimes it's pulse width modulation, pulse. We will discuss those things. And after this pulse modulation, each message symbol or channel symbol takes the form of baseband waveform. This is the basic point. That means, see, after this pulse modulation, whether it is a pulse coded modulation waveform, or if I do some sort of a M-ary pulse amplitude modulation, pulse position modulation, pulse width modulation for M more than 2, then finally here this is some sort of a baseband waveform. Okay, baseband pulse like waveform. Okay. Now that means this is some sort of a voltage level, and that And when you are generating these pulses, actually, many a times what we do little bit of means this pulse modulation block allows for a variety of binary and M-ary pulse waveform that we have studied, and we'll see that we'll discuss about usual attributes of this type of waveform, that is of these features of these waveforms, and the filtering with, because in this pulse modulation, that inside there's a filtering block that I have not explained, I have not written here. That means what this filtering does actually, that means filtering within the pulse modulation block, actually we need these filters actually, because we have certain bandwidth requirement, that actually that due to filtering that occupies more than just one bit time. Just to try to understand. Wait, here it's a crucial information. So inside that pulse, you see, that means if I don't do filtering, what will happen? I will have this type of sharp kind of transition. If there's a sharp kind of transition at this, in order to represent 0 or 1 in the electrical actual waveform, then there's a high frequency kind of thing. Your bandwidth requirement is much more. But you have to reduce the bandwidth, because if you demand more bandwidth, it's more cost. Okay. So what I don't want this type of sharp one. Actually, I want this type of smooth transition kind of thing. Now, so that means you need filtering. When you need filtering, say you are basically doing some sort of a 10 kilohertz, 10 kilo samples per second bit stream. So that's why you have put a 0.1 millisecond. But when you do smearing, what will happen? That your symbol, it will cross this limit of 0.1 millisecond, little bit this side, little bit that side. Okay. So your basically that width will increase. Okay. So generally, if you do the filtering, you will see those things actually. That means actually that each pulse, it will be smeared into neighboring bit times, and this is sometimes that means you are shaping the pulses. So these operation we call that pulse shaping operation kind of thing. We have to do, because otherwise you need a huge bandwidth which incurs huge cost. Okay, because I cannot transmit anything sharp. Okay. Now that for an application that involves RF transmission. See, RF is some sort of a, because sometimes you are transmitting through a normal telephone wire. It's all wired communication. That time you don't need RF. Okay, but so for wireless communication you need RF. When you have then there also you cannot just like the transmit this type of pulses. I say with where you are just physical wire communication you are doing. You can transmit through this little bit of pulse shaping and little bit of signal processing, so that if it is go to that side and this side, that means you have to do little bit of sophisticated signal processing. Otherwise, bit error rate will increase. That means you cannot detect here properly that 1-0 business kind of thing. Okay, so you do little bit of signal processing, and finally you are sending the things. Now, if it is in wireless, that means this type of pulse we generally are not supposed to send, and also it is a low frequency waveform. Okay, we generally what we do, that means we do some sort of a bandpass modulation. That means it is required whenever the transmission medium will not support the propagation of pulse logic waveform. That means when this channel means, see, when it is a physical wire, it's a small distance, your signal frequency is small, like speech, you can do all these things. Okay, say normal telephone channel kind of thing. But when you are doing some sort of a long distance transmission where it is not possible, you have to do some sort of a wireless. Then through wireless, your channel may not be favorable for transmitting this type of pulse, even shaped pulse like waveform. Okay, so then for such cases, the medium requires a bandpass waveform. That means it's normally a sinusoidal looking waveform. Okay, where it is here, it is GIT, G0T, G1T, G2T, GMT, M-1T. Here it is some sort of a S0T to SM-1T. Okay. That means what you are doing. your say m bits grouped together, you have say 2 bits grouped together, say m equal to 2, you have 2 to the power m number of different symbols. These are the symbols, not bits. From there you are making some sort of a channel encoding. I am assuming okay u0 to u3, make life simple. Okay, now from there you are generating g0, g1, g2, g3 pulse like waveform. Okay, maybe PCM waveforms. Now you are doing a wireless transmission, so that's why this pulse will not go to the channel. So I have to do a bandpass modulation. That means bandpass modulation means from G0T to G3T, I will generate S0T to S3T. Okay, so and sometimes we say that okay, pulse modulate and bandpass modulate, we put it in one block and directly from the bit stream we generate this thing. That is also it. It is, but philosophically we just break things so that it is all the steps should be clear. Actually. Directly sometimes we do that is from directly from the channel symbols u0 to u3, you just generate s0 to s3. Okay. Now this SIT, these SIT, they are means you have some frequency spread multiple axis for the time being. Forget about these things. This SIT actually it goes through the channel. Say maybe a channel has an impulse response. First of all, that channel I should have a channel kind of delta T type of channel. Okay, then what happens if it is a delta T type of channel, and if I assume that it's an convolution operation of this SIT convolution HCT, and I will get some sort of RT. Then what will happen? Then if it is HCT is the delta T, then I will get directly RT equal to ST. But actually life is not so. Okay. So what basically we are getting some sort of a this. Say I am just not doing anything here. Say these things are not there. So directly it's all one kind of thing. So you are like this. Here it is RT. Okay. So what you are getting? RIT, some sort of a RIT that is equal to your HC, that means channel convolution SIT plus say WT noise. Okay, say I equal to 0 to m minus 1 or 1 to m, whatever you say. Okay. Now that means this RT, this RIT, that means that received waveform, received bandpass waveform, and corrupted by noise. Okay. Now this received signal, that receiver front end, what it does, in the reverse side, the receiver front end, that means RCD, and demodulator provides the down conversion from each bandpass for each bandpass waveform. Okay, so that means what it does generally, you have a bandpass waveform. Now here I told what frequency up conversion. That means this S0T, it is some sort of in a megahertz level. So you just generate to a 2.4 gigahertz level. You are doing for each S0, SM minus 1. You do the frequency translation. And you have received over here. Now basically this actually in a true sense, actually I should not write this. Basically I should here R up conversion, SI up conversion kind of thing. Please try to understand, because and what is my this up conversion is some sort of a frequency up conversion. So you can so here basically actual operation is here your HC. Okay, that is your HC. Now at this point it is not SIT, it is SI up conversion T. It is just frequencies are there. But why I have removed this up conversion? Because you can always recover the by down conversion by multiplying by the same carrier actually. So it is immaterial. Okay. So finally, let me see, you are doing up conversion. Then here you have got R up conversion, RI up conversion, and you have a L means down conversion, LNA, and all these things. So that from there you are getting RI. So I can say that means as up conversion, down conversion, both are there. I am just removing those up conversion, down conversion business. Okay. So I have got directly RIT equal to HCT convolution SIT plus 1. Is it clear? Is it clear? That means my logic. Now this the demodulator, that demodulator means this one. For that demodulator, the input is that RT, or you can say RIT, whatever it is, and it restores RT to an optimally shaped baseband pulse ZT. Please see. Here I have written Z capital T, that is after sampling, that sampling over here. But just after demodulation from this, because you see RT is some sort of a noise corrupted, and also it is impaired by channel impulse response. Channel impulse response is not delta. If it is a clean noise, channel is delta, then RT twist. So you can directly get that from RT. You can, okay, RT is same as some sort of a SIT, but your RT is not same as SIT. But finally you have to find out the same thing, same information what you have sent over here. So that means that demodulate actually that rest from these active noisy versions of SIT. That means it tries to find out. That means it do some sort of a reverse, means cleaning the noise, mitigate the means some sort of a deconvolution, so that this effect of HCT will go out, and finally try to find out some sort of a S prime IT kind of thing, and which is S prime IT means some sort of a ZT actually, and these ZT I will sample at the bit timing. Okay, that's a sample, so that I will get Z0, ZT, Z2T, Z3T at the sample point. Okay, so that is sampling and detect kind of thing, because this is why the detect, because this is some sort of a this is an electrical waveform ZT. That means, see, I have got this type of waveform. ZT is something like that, electrical waveform. Okay, some sort of a 2.5 volt, 0.2 volt, 2.5 volt. Then say next one is 0.2 volt, like that. And from this one, that I am trying to do a logical operation. That means I know that these, see, I know that these are my channel. See, my channel symbols. It's after channel encoding. I know these are my possible channel symbols. Channel symbol cannot be infinity. Say I have 2 bits grouped together, means my channel symbols may be, this channel encode symbol may be U0, U1, U2, U3. So I have after detection, and that means though it is near, so it must be either these 4. Okay. Now, but why this U high hat is written? Because sometimes you may say that actually depending on this ZT, because you could not clean the channel effect and this noise effect clearly, so that it is actually channel symbol is U0, but you have detected as U1 kind of thing. Okay. Then that means you have the demultiplexing. That means that multiplex, demultiplex, if it is a multiple sources using the same thing, I am not considering at this point multiplexing. From this UI2, you have so that means, and now please try to understand, that means from these RT, at this point, this is quite important. From this RT, first you are generating ZT, and then ZT you are sampling it to capital ZT. This RT to ZT, what you do? Basically, you are removed. So that means this ZT means ideally ZT should be equal to SIT. In order to get that ideally, so that means you have to remove the effect of WT, you have to remove the effect of this one. For this one, that means you have to do some filtering. That means filtering to remove the degradation caused by the channel. Okay. This filter, that means which removes the degradation caused by the channel, that filter is called equalizer. Please, channel equalizer or equalizing filter. Please, this is quite important term actually. Equalizer, equalization operation. That means I am assuming why the name equalizer? Equalizer means what? My ideal condition is what? Ideal channel impulse response should be delta T. Now, if you take why the name equalize, actually, that ideal channel response should be delta T, and your noise noise is not there, something like that. Zero means zero variance kind of thing. Okay. So why the name equalizer? If channel is delta T, what is the frequency response of the channel? If you take the delta T, then if I take the Laplace transform of delta T, then it is 1. That means all frequency it is 1. So that means channel is flat in all frequency range. So that's why we say some sort of a equalize. This is just a term actually. Okay. Now, but sometimes please remember this demodulation and detection. Sometimes because sometimes you will see that these are used directly in one block, demodulate and detect. Okay. And when they say that, okay, because directly you are getting this RT and finally you are getting some sort of a channel symbol. All together they are said basically demodulate and detect, demodulate, sample and detect. In one block they just say this. So that's why we decide what is your input and what is your output. Based on that, we decide actually what he is saying inside, because a lot of terms are used interchangeably. Okay, and basically, but detection, please remember, detection is basically a decision-making process where actually finally you will get some sort of a symbol type of thing, some sort of a logical information you are getting. Means outside, means after detect, everything is all logical, beat, symbol, all this logical information. Before this, all this, before the detect, all these electrical waveform, these, that, all these things. Okay. So now this detect, and from there you are doing some sort of a channel decoding. Okay. And channel decoding means I told that, okay, XOR all operations, and you have to do some sort of a inverse operation of those things, and you will get your message symbol, either encryption, decryption. If you do, fine, otherwise forget it. And finally here you are getting source decoding. That means here you are getting some sort of a binary interface. The communication systems effect is basically, actually they say that the communication chain is this right hand side. Okay, and this is some sort of a source encode. Okay, that is also many a times the format and source encode, they say everything as a source encode. Okay, so now the signal processing steps within the, say, some sort of source coding actually produces the analog to digital conversion and removes some sort of source coding means this source coding procedure actually that removes some sort of a redundant information. Okay. Now, say redundancy, just giving you an example. That means when you do some sort of a source encode, say JPEG image, you are just complex. You have taken an image in a camera, digital camera. You are saving it in JPEG, and when you save it as JPEG, so that we know we can model our eye. Okay, because we know what I can see and why I cannot see. Okay. So what will happen? I will remove those things which I cannot see, because that is useless to send it to the other side, because the viewer cannot see those information. So that means that means which is unwanted information. That means source coding produces analog to digital conversion for analog sources. If it is digital source, so fine, and remove certain redundant information. Redundant information means here what we can't see. Okay. And that a typical digital communication system would either use source coding option, both digitizing and compressing the source information, or it would use either simple formatting transformation, that means digitizing alone. Okay. So sometimes they don't do the compression and all these things. Okay. So anyway, and channel coding for a given data rate. Please, this is quite important. Channel coding for a given data rate can reduce the probability of error or reduce the required signal to noise ratio to achieve the desired probability of error at the expense of transmission bandwidth and decoder complexity. Just let me explain this thing. So what? Say this is your some sort of a SNR, signal to noise ratio. Now this is your bit error rate, BER, probability of error, you can say. Generally our plots are like this. Okay, that means if your SNR is more, your probability, let me say you are pumping more SNR, okay, your probability of bit error is, means if you say at this point here, it will move to say somewhere here. Means what? I am just giving an example. Say I am sending you two information. What I am doing, I am sending two information, 0 and 1. Okay. What I am doing, I am saying, and say you are my receiver. I am sending over this network. What I am doing, I am just saying 0, 1. And sometimes, so this is some SNR I have. Now then I am going 0, 1. So I am pumping more SNR. So then if I say very means mildly 0 and 1. So for you, it is difficult to understand that last digit what I have transmitted. Okay. So your bit error, the probability of incurring error at your end, at the receiver side, this is much more. Okay. Then you say, then why suddenly you will go for this type of low SNR business? I always send it to high SNR business. Then your high SNR means your probability of bit error will be somewhere here. But high SNR means, see, at the transmitter side, I am the transmitter. When I am saying 0, 1, like that, I have to pump more energy to the system. So I am running by battery. When I am pumping more power, that means my battery will be drained. So I cannot do that. I cannot waste that much power. So that means the trade-off is, I will reduce my more power. I will rather reserve my power so that my life of the battery will increase. Rather, but on the other side, you have some sort of a bit error rate kind of thing. Below this bit error rate, the probability of error higher than this, then it is very difficult. Means say maybe Shah Rukh Khan's voice may be viewed as a say Katrina Kaif's voice, something like that. So you cannot do that. So in that case, what you have to do, the other optimization is that given this SNR, I will do a sophisticated signal processing so that my bit error rate will not increase above this, something like that. This is the trade-off actually. So there that the channel coding for a given data rate can reduce the probability of error or reduce the required signal to noise ratio to achieve a desired probability of error at the expense of transmission bandwidth or decoder complexity. Okay. Now sometimes this is one option. Sometimes we say no, I will not. So this is one trade-off: probability of error versus your SNR. Sometimes we say no. What I will do, that means I will reduce the probability of bit error, okay, PE, but I will transmit more number of bits. Transmit more number of bits means you need more bandwidth. Okay, more bandwidth. So that means, say I am sending you some, I am just giving an example. I am sending, say this is my 0 and this is my 1. Okay, this is a sharp. Can you see this thing? So this is your logical 0 and this is your logical 1. Okay, this is a sharp transition, lot of high, because if finally channel will not send in this way. No? The channel will, what will do? Channel will do harmonic, fundamental, then third harmonic, then if it is some sort of a zero mean kind of thing. Okay, so so in order to get this type of thing, maybe you have to go up to 25th harmonic, 27th harmonic, 29th harmonic, 31st harmonic, all this. So when you are going to that level, so in order to do this thing, so what will happen? It will unnecessary. It will demand more bandwidth. Now, but bandwidth is costly, so you don't want more bandwidth. But then what you are saying, no, I will only transmit by my bandwidth is not there. You cannot do this thing. You have to transmit with only fundamental and third harmonic. Now, fundamental and third harmonic means what you are sending. You are sending like something like this. and something, and also you have the energy limitation. So you cannot even go average value of this one. That also it will be reduced. Similarly, here also that will also be reduced. So for this is logical 0 and this is logical 1. So now detecting the logical 0 and 1 from this received waveform at the receiver side is much more difficult than the scenario where you are receiving at the receiver side this waveform. Okay. So these are the trade-off kind of thing. This we'll discuss. We'll discuss in a detail in our later classes. So so that's why that channel coding many a times that is used for reducing the probability of bit error rate and sometimes to reduce the SNR ratio to achieve the desired P actually, and at the expense of transmission bandwidth. But when you do the channel coding, then what will happen? Your probability of error will decrease, but your bit error rate will, your bandwidth requirement is increasing because you are sending more bits. Okay. And the frequency spreading that we discussed about, this frequency spreading, basically the frequency spreading can produce a signal that is relatively less vulnerable to interference, because interference can be from other sources, maybe unintentional interference, maybe your enemy likes to jam your signal. Okay. So it is your actually frequency spreading means we will discuss those things. Basically, rather what I am doing, say you are transmitting the signal in say some particular say 2.4 gigahertz band. Rather I am sometimes I am transmitting at 2.41, sometimes I am transmitting at 2.39, sometimes I am transmitting at 4.42. And my receiver, he knows that when I am sending what actually. So you try to understand that means what I am doing in this frequency spreading means say earlier say I am transmitting, so this is my 2.4 gigahertz and I am transmitting in this zone. That is a very, but now what I am doing, I am transmitting sometimes here, sometimes here, sometimes here. That means sometimes 2.4, sometimes 2.35, sometimes 2.5 in this zone. So suddenly your bandwidth requirement is much more. Okay. So that means that frequencies, but it will give you enhanced security. So frequency spreading is one way of enhancing security or privacy of the communication when it is the vulnerable. Okay. So that's it. So for time being, multiple access we will discuss. Multiple access is a bit higher layer task that at this point we don't need those things. So maybe from the next class we discussed about each block in detail. Okay. Thank you very much. Thank you for joining us.